Hi again, this is Mr. Wakefield here. We're looking at simplifying radical expressions now, and also multiplying is going to be a part of that too. That's why it mentions multiplying here. Simplifying radical expressions is the main thing that we're going to be looking at, and let's jump right into a problem here and you'll see what I'm talking about. But the goal when you simplify a radical, and by the way, we're going to get rid of this this thing in parentheses right here. There are no problems 6 through 8 here. You can cross that out. But we are going to be simplifying as the rest of the directions say right here. We're going to do it by something called the factoring method. Okay, and let's jump into it here. Let's look at square root of 27. Now, we don't know what the square root of 27 is. The goal, you guys, is to not put that in your calculator. If you do, you'll get some messy big decimal in there. And not that that's always bad in every math problem, but in this particular math problem where we're supposed to simplify, not make things more complicated with a big nasty decimal, you do not want to just put this into your calculator. Okay. The goal, however, is to come up with something which is equal to this in a more simplified state where the number underneath the radical is smaller than 27. We want to do that for all 5 of these problems here. We want to make the thing that's underneath the radical smaller while still having something that's still equal to the original problem. Let's see how that all works out here. Okay, in other words, there'll be something outside the radical once we're done, and so it'll make it all still equal to the original radical, but the inside of the radical that you end up with will be smaller. Let's see how that goes. So here's what you do. Before we jump any further, we want to factor something out of 27, but what do we want to factor? We can't just factor anything we want. Okay, we have, when we do square roots, it'll be different for cube roots, but when we do square roots, we look at this thing called perfect squares. Okay, you don't need to write this down right now, but you want to be able to have the ability to write it down, say, for example, in a test situation. Let me teach you how I wrote it down so that you can then write it down too at any time that you need to. The way that I produced all these things, you don't need to memorize all this, you guys, okay? That's not the goal. The goal is to realize where I got this list from, and then you can generate the list yourself, okay? I got the list because this is 1 to the second power equal to 1, 2 to the second power equal to 4, 3 to the second power equal to 9, 4 to the second power equal to 16, and then so on. So this is 5 to the second, 6 to the second, 7 to the second. It just keeps on going. 8 to the second, 9 to the second, 10 to the second. And you can keep on going further than that. I just stopped at 100 just because you got to stop sometime. And usually you're not going to have to deal with numbers bigger than that normally anyway. Okay. Now, as far as the variables are concerned, notice that the variables here, they all have an exponent which is a multiple of 2. 2 times 1, 2 times 2, 2 times 3, 2 times 4, and so on down the line here. Okay, these are the things, and I think you can see now how I generated the list in case you need to do it on a test question. Okay, 1 to the second, 2 to the second, 3 to the second, and so on. X to the second, X to the fourth, X to the sixth, 2, 4, 6, multiples of 2 with the exponents. Okay, that's how the list came about. Okay, but you have to grab something from this list when you factor something out of 27. You can't just factor anything you want out of 27. Okay, so what you need to do is you need to find the biggest thing on this list. And since 27 is not a variable, we're just going to look at the left side of the list here, not the variable side. What's the biggest thing on the list that is a factor of 27? Now remember, factors of 27 are numbers that they can't be bigger than 27 because they've got to be something that divides evenly into 27. Okay. Notice that 27 divided by 1 divides evenly. 27 divided by 1 is 27. But we're never going to factor out 1 because that's not going to make it smaller. Remember we said we wanted to make it smaller. Okay, so you're never going to use 1. I just wrote down 1 right there because it's part of the list officially. 1 squared, 2 squared, and so on. Now, 27 divided by 4, that doesn't divide evenly. Okay, there's a remainder, right? And so 4 is not a factor of 27. 27 divided by 9, oh, that divides evenly. 27 divided by 9 is 3, and so 9 is a factor of 27. However, remember what I just said. Don't just pick any factor of 27. pick the largest factor of 27 that's on this list. It has to be on this list, and it has to be the largest factor of the number that you're looking at underneath the radical. Okay. So let's see if one of these other numbers works also that would be bigger than 9. 27 divided by 16. No, that doesn't divide evenly, so 16 is not a factor then. 27 divided by 25. No, that's not a factor because it doesn't divide evenly also. And then all the numbers after that are too big, because remember, you can't be a factor of 27 if you're bigger than 27. Okay, obviously it wouldn't divide evenly. So that means that 9 is the number that we want. So here's what you do. You take 9 and you figure out what you got to multiply 9 by in order for it to still be equal. Remember, we said the answer still has to be equal to the original thing. And so 9 times what is 27, you guys? 9 times 3, right? So you got to have that second part right there to still make it equal. So that's the first step. And all 5 of these problems are going to have a similar process like that. The second step is to then split apart these two radicals. As it says up here, okay, if you have 9 times 3, it has to be multiplication. It can't be 9 plus 3. 9 times 3, you can split it up so you have square root of 9, square root of 3 with multiplication in the middle. Okay, so let's do that. Square root of 9, square root of 3. Okay. So now you have 2 separate radicals. Let me make that, I kind of squeeze that together a little bit too close. Let me make it easier to read for you here. Okay, there we go. That's better. Then what you do once you do that, assuming that you put the perfect square number that's from the list, okay, assuming you put that first, that's the radical you can actually evaluate. There was another video where we evaluated radicals, okay, and anything that's on this list is something that can be evaluated, okay. We know what the square root of 9 is. We can evaluate that. The square root of 9 is 3. And so the square root of 9 is 3. The square root of 3, that part's going to stay the same. Okay, the part that you multiply by after you grab a number from the perfect square list, that second number is going to be, if you do it right, that's going to be something that you can't evaluate. And it's okay to leave that the same, okay? So you can leave the square root of 3 as it is, but take the part that has the number from the list, okay, and actually figure out what that's equal to, because you will be able to. Anytime you got a square root radical, okay, that with one of these numbers underneath it, you can figure out what it's equal to. Square root of 9 is 3, okay, and then square root of 3 stays the square root of 3. There's still multiplication in between here. You don't need to write the multiplication symbol anymore, because when you shove a number next to a radical, it's already implied that that's multiplied. You could put the multiplication dot in between still if you want, but you don't have to. So the square root of 9 became the 3 right there, because that's what it's equal to. Square root of 9 is 3. And then the second part stays the same. So that's the goal here. Okay, figure out what you're going to factor out. Something from the list that's the biggest number on the list that you can factor out. Figure out what it's multiplied by. You then split it up into 2 separate radicals. You then figure out what the first radical is equal to. Okay, and that's all you got to do. Let's do that again. This time, however, there's going to be 2 different things you got to factor out, because there's a number, a coefficient number, but then there's also a variable part. So let's do one part at a time here. Let's start out with the 48. Okay. What's the biggest number on the list that can be factored out of 48? Again, we're not going to do 1 because that's not going to make it smaller. 48 divided by 4, that does divide evenly. Okay, so 4 is a factor of 48, but is it the biggest one on the list that's a factor of 48? That's the question. 48 divided by 9, no, that's not a factor because it doesn't divide evenly. 48 divided by 16, remember, have your calculator handy to figure these things out. Your calculator will tell you that 48 divided by 16 is equal to 3, no remainder, so it's a factor. So 16 might be the answer. Let's find out. Let's see if there's anything bigger than 16 that works. 48 divided by 25. No, that's if your answer in your calculator, when you say 48 divided by 25, if the answer is a decimal, you know that it's going to not divide evenly. It needs to be a nice whole number, you know, like 1, 2, 3, 4, something like that. 48 divided by 36, no, that's going to be a decimal. And then everything else is too big, bigger than 48. So 16 must be the correct number that you're going to factor out. Now, the reason why I made a big radical right here is because we still have to do x to the 5th. Now, the way variables work in general is that any exponent, it doesn't have to be a factor of 5. That's not how it works with the exponents. With the exponents, you just have to pick a exponent that is not bigger than 5. It could be equal to 5 if 5 was on this list. 5 is not on this list, but if it was, you could use that. But you can pick an exponent that just makes sure it's not bigger than 5, but it also has to be the biggest thing that you can pick, just like over here. So here's the big question. What's the biggest exponent that's not bigger than 5? The biggest exponent, again, you got to pick the biggest thing, just like over here, that's not bigger than 5. Wouldn't that be x to the 4th? Because x to the 6th is bigger than 5, bigger than x to the 5th. So I picked the biggest exponent that was not bigger than the exponent 5 right here. Okay. So that's what you do. You do it for 48. You look at the left side of the list because there's no variables there with the 48. And then when you get to the variable part, you look at the variable part of the list and you pick the biggest exponent that's not bigger than the exponent you already have. Okay, now what you do is the same thing you did over here in the first problem, okay, is you figure out what's being multiplied by 16x to the 4th in order to still be equal to 48x to the 5th. When you factor a term out of another term, it's kind of similar to something from another video right here. Let's review. It's kind of like right here where we have this problem where you factored out 2x, okay, and then you got to figure out what to multiply by in order to still make it equal, like we have to in our current problems right now, equal to this problem up here. So 2x times what is 2x to the 3rd? We figured that out right here. 2x times what is equal to negative 72x? We figured that out right here. And it's done in the same way, where you have 16 times what is equal to 48. Well, 16 times 3 is 48. Okay, we know that because 48 divided by 16 is 3 in your calculator. So you can figure it out that way as well. Okay, 48 divided by 16 is 3, so 16 times 3 is 48. And then remember, when you have variables, if they're the same, you add the exponents. So wouldn't it make sense to say x to the 1st right here? Because x to the 4th times x to the 1st would be 4 plus 1 with the exponents, adding the exponents when you're multiplying the x's. 4 plus 1 is 5, and so it matches up. Okay, so that's the reason why 3x is the thing you're multiplying by. But you got to put this 3x here, okay, just like we had to put this 3 right here after we figured out what went inside of the radical from the list that we have here, okay? Now, we then split it apart just like we did in the last problem. Split it apart. 16x to the 4th goes inside of one radical. 3x goes inside of the other one. And then just like we did in the last problem, you figure out what the first radical is equal to. And then the second one, that stays the same, just like it did over here. So what is the square root of 16x to the 4th? Okay, in other words, what thing is taken to the second power that's equal to 16x to the 4th? Okay. Looking at a problem from a different video right here, it's kind of like this problem right here where it's the square root of 36x to the 8th. What thing is taken to the second power to equal 36x to the 8th? The answer is 6x to the 4th, which is where this answer came from. It's because 6 to the second power is 36, And then when you have a variable, you multiply the exponents, the one on the inside and the one on the outside. And so 4 had to be the correct exponent because 4 times 2 is 8. Excuse me. So this answer was 6x to the 4th, but now let's, in the same way, let's figure out what this answer is here. Okay, isn't it true that 4 to the 2nd power is equal to 16? Remember the coefficient part, not the variable part. That part you actually take it to the 2nd power. You don't do 4 times 2. Okay, but then when you get to the variable part, you've got to multiply the exponents in order to make sure it matches up with the 4. We know that 2 times 2 is 4 here. 2 times 2 is 4, so the missing exponent right there that goes inside the bracket is 2, and therefore 4x squared is the thing that you have to take to the 2nd power to equal 16x to the 4th. And so just like in the last problem, you figure out what the first radical is equal to, and the second radical stays the same. Okay? Let's do one more as far as square roots go, and then we'll talk about cube roots. This one has no coefficient, no visible coefficient, which means the coefficient is 1. When the coefficient's an invisible 1 right there, you don't need to do that part. Okay, let's just jump right to the y to the 5th, but we have 2 variables this time. When you have more than one variable, you just you use the right side of the list twice. Okay, it doesn't have to be an x. This could actually be any letter. It could be y to the 2nd, y to the 4th, y to the 6th, and so on. It could also be z to the 2nd, z to the 4th, z to the 6th, and so on. And so we can do that. We can use that list for both the y and the z here. Let's go ahead and give it a try. So y to the 5th is, again, you're looking for the biggest exponent on the list that's not bigger than 5. Just like in the last problem, that would be y to the 4th, because y to the 6th would be too big. Z to the 6th, however, what's the biggest exponent that's not bigger than 6? It could be equal to 6. That's okay. Just can't be bigger. And so that would be z to the 6th. Okay, again, the same exponent, using the same exponent as what's on the list. That's okay. Just don't pick an exponent that's bigger. Okay, pick the biggest exponent that's not bigger than the exponent that you have. Okay, but remember, we have to multiply by a second part right here, just like we did in the first 2 problems, so that it's still equal to y to the 5th, z to the 6th. Remember, there's no coefficient, so you don't need to do that part. Okay, but y to the 4th times what is equal to y to the 5th? Okay, if you're multiplying by something in order to get a bigger exponent, you want to put that same variable down again here, just like we were doing when we were talking a few minutes ago about the greatest common factor problems, factoring something out. Okay, you've got to add the exponents to make sure they match up with the 5. So that would be y to the 1st right there. You don't need to write the 1. Okay, but y to the 4th times y to the 1st, 4 times 1, or 4 plus 1 is equal to 5. So it matches up. Now, z to the 6th, if it's the same exponent, do not put another z over here. Just don't do the z part. Because if you do, then you'll end up with 6 plus something, and it will be bigger than 6. It won't work. So if the exponents are the same, don't put the z there. Okay? So we once again have 2 different parts. We split it apart like this, just like we did in the first couple problems, like that. The first part and the second part. And then we figure out what the first part is equal to because it has the stuff from the list. You can always figure out that first radical because it's got the stuff that's on the list. Okay, that's why they call them perfect squares. We can figure out what the square roots of those things are. So what thing, you guys, is taken to the 2nd power that's equal to y to the 4th z to the 6th? Okay, again, you don't need to do the coefficient part because there's no visible coefficient here. Okay, in other words, it's equal to 1. But we need to do the variable parts. Okay, 2 times 2 is 4, so y squared must be the thing that I put inside in order for y to the 4th to be over here. Okay, and then z to the what? Z to the 3rd would work, wouldn't it? Because 3 times 2 is 6. And so z to the third must be the correct thing to put in there. And so once again, we figure out that the first radical is equal to y to the second z to the third. We figured out the first radical. We kept the second radical the same, square root of y. And that's what you do when you're simplifying radicals. And we end up with a radical that is, we end up with a radical in the final answer that is smaller than the original thing that was underneath the radical up here. Okay. But you need, again, you need to factor out, in order for it to be completely simplified, you need to factor out the largest thing that will come off the list that can be factored out. Okay. The good news here with these last two problems is that it's exactly the same process, even though it's a cube root. The only difference is that we have a new list. That's the only difference. There's a new list. When we're doing cube roots, we look at what we call perfect cubes instead of perfect squares. And you can generate, say if you're on a test, you can write down on a piece of scratch paper. You have to wait until after the test starts because we can't have cheat sheets on tests and stuff like that. We can't have formula sheets or anything. But you can write down this after the test starts. 1 to the third, 2 to the third, 3 to the third, that's what all these are equal to, 4 to the third, 5 to the third, just like on the other list where it was 1 to the second, 2 to the second, 3 to the third, and so on. This is 1 to the third, 2 to the third, 3 to the third, and so on. And notice here that just like on the front where it was multiples of 2, 2 times 1, 2 times 2, 2 times 3, and so on, the exponents now are 3 times 1, 3 times 2, 3 times 3, and so on. And so just like square roots had multiples of 2, cube roots have multiples of 3. Okay, so numbers taken to the third power over here on the left, and then exponents that are multiples of 3 on the right. 3 times 1, 3 times 2, and so on. Okay, let's go ahead and try it. But again, the process is exactly the same steps. It's just you're looking at a different list. So we still have to find the largest thing on the list that will factor out a 48. It's just that we're looking at the cube list. Make sure you're looking at the correct list. And the way you know if you're looking at the correct list, you look at what the root is. Is it a cube root or is it a square root? Okay. For now, anyway, we're not going to be looking at fourth root or fifth root of one of those bigger roots. Just square roots and cube roots. So with cube roots, we're looking at the perfect cube list. What is the biggest number on this list that is a factor of 48? Again, we're not going to do 1 like we said because that's not going to make it smaller. 48 divided by 8 does divide evenly, though. But how about 27? Does that work also for 48? No, it doesn't. 48 divided by 27 does not divide evenly. Okay, and then everything else is too big. So 8 is the correct thing that you factor out. It's the biggest thing on the list. It's a factor of 48. 8 times what is 48, you guys? Because remember, it still has to equal 48 when you do the two parts here. 8 times 6, right? So just like in the previous problems, you now split it apart. But remember, since this is a cube root, when you split it apart, you guys, both of the radicals, this is hard to remember sometimes, so be careful. Both of the radicals have to be cube roots. So if you have a cube root and it splits apart into two radicals, both of the new radicals are also cube roots. Remembering to write those little 3's is sometimes the toughest thing to remember. Okay, sometimes you get in a hurry or something. Okay, and those 3's are very important because if you don't write them, it looks like a square root when there's no number there, right? So very important you write those 3's. And then just like in the problems up here in problems A, B, and C, you now figure out what the first radical is equal to, leave the second radical the same, and then you're done. We know that the cube root of 8 is 2 because we know that 2 to the third is equal to 8, and so likewise the third root of 8 is 2. And so for that reason, we get 2 as the answer to the first radical. Once again, the second radical stays the same, and you're done. So you can see the process is the same. Okay, you factor out what you need to factor out, you split it apart after that, and then you figure out what the first radical is equal to. It's the same thing here. Let's do that one more time with the cube root here. This time we have 3 parts. when you have a coefficient and you have variables, each part is a separate part. If you have more than one variable, then each variable is a separate part. So that's why we have 3 parts here. So we do the same thing we did up here in problem B and problem C, where we look at each part separately, looking at the list. So let's go through it carefully here. Okay. 8, this is kind of an interesting one here. 8 works for 8. Okay, you could do the same number. You just remember, since it's a factor, it can't be bigger than 8. But 8 divided by 8 does divide evenly. It's equal to 1. And so 8 is a factor of 8. You can factor that out. But you might be wondering, hey, what would I put over here eventually? We'll get to that in a minute. Okay, you don't need to figure that out yet. Okay, remember, we want to do all 3 parts here, and then we'll figure out what to multiply by. But yes, 8 is a factor of 8. Okay, the same number is always a factor if it's on the list. Now let's go to the variable parts. What's the biggest exponent on the list? Let me move this over here. What's the biggest number? What's the biggest exponent on the list that's not bigger than 4 for x to the 4th? Wouldn't that be x to the 3rd? Because x to the 6th, which is the next thing on the list, that's too big for 4, right? Okay, now how about y to the 8th? Okay, 3 and 6 are both not bigger than 8. Okay, but 9 is bigger than 8. So 6 would be the one you want to pick, the biggest one that is not bigger than 8. But remember, that's y, so you got to do y to the 6th, not x to the 6th. Okay? Now, so we did each part. We factored something out from the list for each part, and then we figure out what to multiply by in order to still make sure that it's still equal to the original thing here. Okay? So 8x to the 3rd y to the 6th times what is equal to this? Well, 8 times 1 is equal to 8. And so the 1 would go there, just like when we did 16 times 3 is 48. 8 divided by 8 is 1, and so 8 times 1 is 8. Okay? You might be wondering, do I really need to write the 1 there? No, you don't, because when you multiply by 1, it doesn't really make any difference, right? It's still the same thing. Okay? But I just wrote it there just to, since we're learning this just now, reviewing it, learning it, all that right now, that just wanted to make sure that we stick with the process here to make it easier to follow. How about x to the 3rd and y to the 6th? Remember, just like up here, you got to find the right exponent that adds to the current exponent to make it equal to the exponent up here. 3 plus what is equal to x to the 4th? Okay, that would be, and again, it's got to be the same variable there, so I got to bring the x down, but it's going to be x to the 1st, right? 3 plus 1 is 4. And then, just like what we did up here with z to the 6th, when the exponents, oh, I'm sorry, I read that wrong. My fault there. I thought that was a y to the 6th right there. That's y to the 8th. So 6 plus what, you guys, is equal to 8. 6 plus 2 is 8. And so we're going to do y to the 2nd right there, like that. Okay. And so once again, you can erase off that 1 if you want. You don't have to. You're not going to be marked down. There's nothing wrong with keeping the 1 there. I'm just going to erase it just to make it look a little bit simpler here. Okay. But 1 times xy squared is the same thing as just xy squared. Okay. In other words, when your coefficient is 1, it can be invisible. Once again, we'll split this apart. Okay. Just like we've been doing, into 2 separate radicals. Don't forget to do those little 3's for each part because this is a cube root problem. And then once again, we figure out what the first radical is equal to, keeping the second radical the same. So we want to know what is taken to the 3rd power. Again, it's 3rd power because this is a 3rd root, cube root. What is taken to the 3rd power to equal 8x to the 3rd y to the 6th? That would be 2 to the 3rd is 8. It would be x to the 1st, 1 times 3 is 3. And then it would be y to the 2nd because 2 times 3 is 6. And so the thing that this radical is equal to is equal to 2x y to the 2nd Okay, this radical is equal to just that. No, the radical is gone now. You figured out, you evaluated the radical. You figured out what was taken to the third power to equal that. So that radical is gone because we figured it out. We figured out what the cube root was equal to. And then the second radical stays the same, right? Just like we've been doing. And so that is simplifying radicals, you guys. Okay? Again, please remember that the process is the same whether it's a square root or cube root, but please remember two key things here that are easy to forget. First of all, when you're doing cube roots, look at the perfect cube list. When you're doing square roots, make sure you're looking at the other list, the perfect square list. And then also remember that when you have the cube root, to keep on writing those little threes as you go down where the index number goes for the radical. Okay? And that concludes simplifying radicals.